Hello everyone, I'm Palvi Aggarwal. I'm a postdoc researcher at Carnegie Mellon. Today I'll be presenting our research work on masking strategies of cyber deception using CyberVan. So as we all know that attackers gather information about target before launching an attack during network reconnaissance phase. And cyber defenders could use this opportunity to deceive attackers using masking during this reconnaissance process and provide some falsified information. So they could change certain attributes of a system such as operating system, ports open and name of these services and mislead attackers. To do this strategically, Shankar et al. 2018 developed a zero-sum Stackelberg security game that basically associates systems to configuration to observed configuration that minimize the utility of attacker. Let's take an example. Say attacker is trying to exploit Nginx, and to do that, if there is no deception in the network, attacker would easily scan all the machines, find the service and attack. However, if defender is using deception and mask these two configuration to some observable configuration, then attacker will have to test its exploit on all the systems in order to be successful. So this will increase, lot of efforts and time for attacker, and that will be benefit of a defender. Using that zero-sum Stackelberg security game, we use optimal as well as random conditions as our defense strategies. So random is nothing but where these TCs are masked to some observable configuration just randomly. There's no strategy behind that. However, in the optimal case, these are strategically masked. TCs are strategically masked to observable configuration, keeping the objective function in mind that we need to minimize attackers' utility. So these are the 5 metrics that represents our defense strategy, and rows represent true configuration and columns represent observable configuration. So taking an example that here FreeBSD, there are 5 FreeBSDs which are used as observable configuration. And what happens here is Ubuntu 8 is and Avaya gateway. So there are 3 Avaya gateway and 2 are Ubuntu 8. And each TC is associated with some kind of utility value. And if say attacker is exploiting these machines and the expected value of Avaya gateway is 3.6 and Ubuntu 8 is 2, we expect that rational attackers would go for FreeBSD instead of Ubuntu 8 given the expected value is higher. So to test this hypothesis, what we do is we conduct an exploratory study in CyberVan, which is Cyber Virtual Ad Hoc Network, that provides ability to run human-in-the-loop experiments. And we were provided with several virtual machines where we deployed deception strategies. And then we hired human attackers to interact with these strategies. So in this experiments, there were two between subject condition, optimal masking and random masking. And these two conditions I already explained in earlier slides. So we hired 30 participants using a pre-screening test, which is evaluating their cybersecurity knowledge. If they pass the test, then they were allowed to participate in the experiment. So we selected these 30 participants and randomly assigned them to optimal and random condition. Goal of this attacker participant in this task was to maximize their payoffs over the 5 rounds. So in this task, there were total 6 rounds, 1 practice and 5 real rounds. And each round has different 5 metrics. And the utility of 2 configurations were given in the experiment, and which was same throughout the rounds. Participants were paid $18 as base pay, and they could earn up to $7.5 for their attacks if they are successful in over the 5 rounds. So each round consists of basically 2 phases. One is exploration phase and another is exploitation phase. During the exploration phase, they basically scan these machines using Nmap OS fingerprinting, and they scan this machine and know about what is the observable configuration of this system, and learn about open operating system ports and services through scanning. Once they scan all the machines, then they go to exploitation phase, where they decide which IP address they want to attack and what kind of exploit they want to use. So if their exploit is matching with the true configuration, they will earn points because they will be successful in that case. And this table was provided throughout the experiment. And if they fail the attack, and then they will get 0 points. After collecting the data, we looked at their success rate and average points. And we first, looking at the success rate, what we found that optimal condition was more successful for attackers compared to random condition, and we were a bit surprised that why that is happening. Then we looked at their average points, and what we found that optimal condition, attackers were gaining less points compared to random condition. And then we found that, okay, they were more successful in launching the attacks. However, their attacks were moving towards more lower value machines compared to high value machines. We also observed that their points earned are in both optimal as well as in random condition are quite less than what is expected from a rational adversary. To further investigate that why they are moving towards low value machines in optimal strategy, we looked at what kind of true configurations they are attacking. So in this graph, what we see that on x-axis is the true configuration, which is sorted by expected value. Left side is the lowest expected value, and right side is the highest expected value. These are separated by rounds, and y-axis represent the frequency of attack. On top of each bar, we represent the value of machine and probability of being successful in attack on that particular machine. So what we observed in both optimal and random condition, that there is some kind of certainty bias and risk averseness in human participants, human attackers. That's why they are going for more sure options or high probability of success compared to high value of machines. So what we see say in round one for optimal strategy, attackers are attacking more slackware machine, which is only worth 2 points compared to any other machine in that particular round, which is 8, 6, and 15 points. So this gives us some ideas that they have some kind of certainty bias, or they want to go for sure option where the success is higher. So throughout this study, what we learned is that human attackers gain lower points than expected rational adversaries. So they are clearly irrational in their decision making. And we also learned that there is a certainty bias, or we can call it risk aversion in their decision making. And that's why they are preferring probability of success compared to potential rewards. Using these learnings, we develop a new masking strategy informing this risk-averse behavior to this Stackelberg security game, and develop new masking strategies. And we recently collected human data on these new strategies. And another thing what we have been doing is developing instance-based learning theory models, so that we can have a computational representation of attackers' decision making. So this computational representation would help us generate a lot of synthetic data, which could be used to test new masking strategies, and it can offset the cost of running human experiments in such complex scenarios. So we are looking forward to analyze our latest results and see the performance of cognitive model. Thank you so much.